I brought this class materials from the Professor Luca de Alfero's class because I think that one is more organizable. And you can also watch the you can also read the textbook from the website. And I will send you, if you want, I will send you this textbook link later. So the first one, I will probably just introduce some ideas of recursions, because I remember in the last section of I don't remember it's lab 1 or lab 2. There's some ideas about the recursion. So let's just review the recursion first. Actually, from the mathematical point of view, recursion is here are some 3 examples. For example, like the factorial. The factorial is the first idea of building of recursion. So you can just simply define a function like this. You just calculate the recursion by multiple multiplications, right? But you can also call the function itself. That's a recursion, right? So you can also define the recursion. You can write a function in a recursion way, like say factorial recursion. If the initial value n equals 0, then your output is 1. Otherwise, your output is n multiplied the factorial of n minus 1. Okay. So given a 5, I assume in this way, the recursion way, this function is called much more faster than the previous one. And for each recursion function, there's a feature you should notice is how to determine this recursion. Because if you're continuously call this function, it will never end. It's just like a while loop, right? So, so for example, if you're define a function like a factorial never ending, you just call the n values continuously. Let's just try to run it. Well, it doesn't cause this function, but similar to the other way of represent factorial of n is factorial of n equals factorial of n plus 1 divide n plus 1. So here we have in the function we have n. The other one we have n plus 1, which is large or equal to the n, right? So in these 2 types of function, even though we write in a recursion way, it will probably not gonna ending, right? So in that way, we have a conclusion that if you want to terminate a recursion, we always want to call the subfunction in a value smaller than the previous one. Let's say in the internal of this function cos n, we always call some values less than n, right? For example, like we cos n minus 1. In the previous one, in the previous iterative function, here we can see what we call is n minus 1 rather than n or n plus 1. There's 2 other examples of recursive function. One of which is called Peano Arithmetic. It's a way, I think it's a recursive way of adding numbers. Yeah. So the definition is if the added number m is 0, so n plus m equals n. Otherwise, if we add a new number m to the n, so if it's n plus m equals 1 plus n plus m minus 1. So this is recursively called a m minus 1. step by step. So 1 minus 1, 1 minus m minus 1, m minus 2, step by step. So similarly to the factorial function, so if m is not equals to 0, we always call this 1 plus piano add m minus 1. So this is 4 plus 5 is 9. This is an example of list an array. I won't show this, but the idea is similar to the previous examples. The last one is Fibonacci numbers. Fibonacci number is quite similar to be simple to be understand. It means the current values equals to the previous two values added together. So what you need to give is the initial 0 and initial 1. So then you can calculate each numbers larger than 1, right? So 2 is 0 plus 1. So here the recursive call is the Fibonacci m minus 1 plus Fibonacci m minus 2. So the termination condition still holds, which is smaller than the n, right? So the Fibonacci number of 10 is 55 here. Here is, I think it's a way to calculate how much cost of Fibonacci numbers, a calculation of Fibonacci numbers. Yeah. The last one is a Euclidean algorithm. The Euclidean algorithm is I think it's the most ancient algorithm to calculate the common divisor between two numbers, m and n. So this is the definition of Euclidean algorithm. So it has, if n equals 0, then return the m. Otherwise, return the m modulus n and n. The function, the input function is m modulus n and n. So what you need to do is just call this MCD function again here, m modulus n and n. The last one is the permutations. I won't show you the permutation example because it's not a calculation. It's an example of sets or permutations. But I think the idea is similar. I will post this Jupyter notebooks later, and if you want, you can just review these materials.